All righty. So I think last time we stopped around here, it was actually on this plate. We were talking about the signs of delta G and spontaneity of reactions and stuff like that. We just a real quick recap of some of the stuff that we looked at already. We took the second law of thermodynamics and we reformatted it in the form of the Gibbs-Helmholtz equation, which introduces Gibbs free energy, and that's related to the change in the entropy of the universe. And its sign dictates the spontaneity of a process. When the sign comes out negative, that means the delta S of the universe is positive, and therefore, on a thermodynamic basis, that process is predicted to be spontaneous, which also implies that if the delta H comes out to be positive, then the opposite process is spontaneous. And then the last choice is when delta G comes out to be zero, and somehow that's associated with equilibrium. So we looked at some specific delta H, delta S, and delta G for this phase transition of ice to liquid water. And we didn't look at any specific values, but we could have calculated these based off of the published values in your textbook. And just to kind of cement this a little further, I want to ask you a question. Now, this reaction is for the melting of ice to water. Do you remember from Chem 200 what the opposite, I'm sorry, what the delta H for that process is called when you melt a solid? It has a specific name to it.
I just remember there's like a delta H of vaporization, but I can't remember the one for melting.
Bingo. Good job, man. That's right. So there's a delta H of vaporization for the transition from liquid to gas. This one is a solid to liquid. Does anybody remember what it's called? All right, no, it's delta H of fusion. Okay, so this delta H has a specific name that we give it, and it's associated with that transition temperature for, in this case, melting of ice. So this delta H is specific. So if you see it in a problem, like the delta H of vaporization or the delta H of fusion, that's just the delta H for that transition. Okay, so you can keep that in mind. And we talked about a lot of other ins and outs of this plate. And then we moved on to this one and we said, okay, well, let's look at just some reaction. And we talked about how iron naturally rusts, and this is rust iron oxide. And so you would think that the delta G for this process is positive, which means it's the spontaneity of the reaction is the reverse. And sure enough, it is. And that was calculated just using your book values and those equations that we introduced for the delta H of reaction and the delta S of reaction. So we find out that it is in fact positive. But just as before in our conversation back here, when we were looking at transition temperatures for this specific reaction of the melting of water, or delta H of fusion is involved. For something like this, we can also calculate a tipping point temperature or a transition temperature. Like where there would be an equilibrium between the reactants and the products. And you see, it's not a change in phase kind of thing, but it's a temperature where there's an equilibrium between the reactants and the products. And since this is one of those cases where the spontaneity of the reaction is temperature dependent, we can find that tipping point temperature and then say something like any temperature above that um, will make this reaction, say, spontaneous, or make it non-spontaneous and spontaneous in the opposite direction. So that's referring to these two cases on this plate here that are temperature dependent. And we saw that the temperature dependent cases are when delta H and delta S have the same sign. Either they're both positive and both negative. And when you look at it that way and you go back to this equation here, you can see how temperature is involved when, for example, delta H is negative, if this is a negative term, and delta S is negative, because of this negative sign here, these two magnitudes are fighting against each other. And whichever one has the higher magnitude is going to win at that temperature. So you can see that there must be a temperature that's so low that this term is going to win out. And conversely, there's probably a temperature that's high when this whole term over here is going to win out. So it's a balancing act between those two terms when delta H and delta S have the same sign. So any questions on that? Do you guys understand that? All right. Then let's go back to where we left off last time and take a look at this tipping point temperature. So we have some reaction, which we can calculate the delta H and the delta S for, and therefore we can calculate delta G for the reaction and see that at this temperature, standard temperature, the reaction is non-spontaneous. All right. So the question then is, or maybe a follow-up question could be, what temperature will we need to cook this baby up to make the reverse spontaneous? Well, first of all, we have to see if it's possible. And in this case, both delta H and delta S are positive. They have the same sign. So this is a case where the process is temperature dependent. So we can go back to our equation and say, well, we can calculate that tipping point temperature by sticking in a 0 for delta G, because we know that signifies an equilibrium between reactants and products. And once we do that, we can then calculate T, knowing delta H and delta S. And we do know those right here and right here. And so then we go along and we plug in those, solve for T, and we find that tipping point temperature. Now, does anybody see a possible problem in this logic? So everybody believes this is true? Is anybody out there? All right, let me see. Yes, there are people there. So what do you think? The cat's got your tongue. It's like pulling teeth with you guys. So maybe we should just go around the virtual room and see how people are doing. Guys?
I'm not sure.
Okay, good. Thanks for saying something. I don't even know if there's something wrong with my connection or what's going on. You guys seem like you're as tired as I am. All right. So w- one of the things here, I mean, and it's a subtle point, and I don't think your book talks about it, or most general chemistry textbooks talk about it, but we're calculating this temperature here um, using the Gibbs-Helmholtz equation, plugging in a 0. But check out, these are delta H superscript 0. What does that signify right there?
At room temperature.
Yeah, so it's at standard temperature and all the other conditions. And now we're calculating a temperature for a transition that's not at standard, but we're using the values that are standard values. So this is probably, using this equation for this is probably just an estimation, and it assumes that delta H and delta S are pretty much constant with temperature, at least through this range. So there's an assumption in here that's kind of buried, and that is the assumption that the delta H and the delta S is fairly constant with temperature, and that may or may not be true. It's kind of outside of the realm of this course, because if we had a temperature dependent delta H, it would be much more complicated, and it would probably involve some integration over a temperature range and heat capacities and things like that. And so that's more of a physical chemistry type of a class. So we just assume now that it's constant over temperature. We use those values, and this is really an estimation. But anyway, after finding that transition temperature, what temperature can I set this reaction at and then know that it'll be spontaneous? Does anybody know what temperature it needs to be spontaneous as written? In other words, the reactants are going to form products without external influence. Anybody know what temperature it needs to be? At 25 degrees, delta G is plus 300. So what does that mean at 25 degrees?
298 Kelvin.
Yep, at 298 Kelvin. So is this reaction spontaneous at 298 Kelvin?
No, because it's a positive.
All right. So what temperature would it be spontaneous at? How about this calculation down here? Why do we do that? You guys are sleepy today. Yeah, so we did this calculation down here to calculate that that tipping point temperature. So this temperature refers to when delta G is 0. So this is when there's a equilibrium between the reactants and the products. And that also signifies that the magnitude of the delta H, and it's positive, is the same as the magnitude of T times delta S, right? So that makes it 0. Now, which way would I need to make the temperature go to change that 0 into a negative and therefore make it a spontaneous reaction? Do I go up in temperature or down?
Up?
Yeah. And if I went up, right, that would make this T larger. That would make this whole term bigger, and it's negative, and then that would carry the sign of delta G over into the negative area and make that reaction spontaneous. Does everybody see that?
Yeah.
Okay, good. Any questions on that? Any questions on anything?
Um, so the temperature would have to be greater than 835.1.
Yeah, thank you for saying that, because if a question says, at what temperature would this reaction be spontaneous? You can go through and do this calculation and come up with this temperature, but that wouldn't be the answer. The answer would be any temperature greater than that value is going to make delta G negative and therefore spontaneous. Okay. All right. Now we saw that there's two ways. Well, there's one way so far to calculate delta G, and that's through the Gibbs-Helmholtz equation, that one that looks like this here, where delta G equals delta H minus T delta S. There's another way to calculate delta G, and that's using um, the idea of the delta G of formation of reactants and products, very similar to what we did with delta H. So we invoke this idea of the delta G of formation, and we assign all the elements in their standard states at 25 degrees Celsius as having a delta G of formation of 0. So then we can find all the delta G of formations of other compounds that aren't in their standard states and tabulate them. And so they're also tabulated in your textbook. And it might be worth taking a look at a table. Let's see if I can find one online. All right, so this is pretty much a typical table that you'll find online, maybe even in your textbook. So you have a bunch of compounds uh, here they call species because sometimes they're compounds, sometimes they're just elements and so forth. And then you have the columns for delta H of formation. You have absolute entropy values, and those things are possible because of the third law of thermodynamics that sets the 0. And then we have the last column is a delta G of formation value for all these species. Notice the typical units that they use for each one of these. For delta H and delta G, it's almost always kilojoules per mole. Okay. S is joules per mole and then a degree Kelvin in there because of how you calculate S and delta S. It's a temperature dependent kind of thing. And it's in joules, not kilojoules. When we go down, we see this first one right off the bat, aluminum solid. Well, that's the way it exists under standard conditions. So it's not going to cost us any heat energy to form them. And it's also has a change in Gibbs free energy of formation of 0 by definition, because that's the way it exists naturally. As opposed to entropy, we don't have a 0 value for aluminum. And other species that exist in standard conditions will also have zeros, like bromine liquid. That's going to have a delta H of formation of 0 and a delta G of formation of 0. Calcium solid will as well, and so forth. So sometimes you won't even see these tabulated for those values. And you'll just have to know that they're 0. All right. So now we define a similar equation for calculating the delta G under standard conditions for some reaction. And you see it has the same form as our delta H and delta S for reactions. Whereas, delta S here, I mean, we won't have a delta S here. It'll be absolute entropy value because we didn't define any delta S of formation. We didn't need to. The standard states for Gibbs free energy, again, the ones that we used before for delta H, any gases have to be at 1 atmosphere. Now we introduce concentrations of solutions. So the standard concentration for a solution is 1 molar. And the delta G of formation is 0 for these guys. Okay. Any questions on that? All right. Here's an example of how to use those tables. So in those tables, you would look up the delta G of formation of the products, multiply them by their stoichiometric coefficients, and add them all up. Know that, again, just to remind you, that nitrogen gas, that's in its standard state, so that's going to have a delta G of formation of 0. So you add all those up, and then you subtract out the reactants to get the difference. Again, this is going to be 0 here. So you can calculate a delta G for a reaction directly using that equation and those tabulated values in your textbook or online. Sometimes people will refer to a process being spontaneous because they've narrowed down which one of those parts in the Gibbs-Helmholtz equation wins out the day and changes the sign of delta G to negative. So if you look at the Gibbs-Helmholtz equation, which is not here readily, let me just write it up here. So we know that delta G equals delta H minus T delta S. And so if we want delta G to be negative, that comes from 2 possible contributions. If the 2 are in, if they're opposite signs, and we have those those cases that when delta H and delta S are the same signs, that means that because of this negative here, this term is going to have an opposite sign from this term. Okay, so they'll be working against each other as far as the overall sign of delta G. So when we have a case where they're both negative, as in this example, I have a negative delta H reaction, and I have a negative delta S reaction, then I know this is a case where it's temperature dependent, and those two magnitudes are going to fight up against each other to see who wins out the day and dictates the sign of delta G. So in this case, you see that this delta H is negative and larger in magnitude than the delta S contribution to the delta G. And so we say that this reaction is spontaneous because delta G is negative. And the reason why it's spontaneous is because the enthalpy is negative and it's larger in magnitude. So you'll see sometimes this expression that this reaction is enthalpy driven. And that's because of the exothermicity of delta H. But don't be fooled. That exothermicity or that heat goes into the surroundings and increases the entropy of the surroundings. So the second law of thermo is still at play. The delta S of the universe has to increase, and it's a sum of the system and the surroundings. Even though sometimes we get lost in the forest and we can't, or we get lost in there and we can't see the forest from the trees. But anyway, sometimes you'll see this terminology of enthalpy driven, or in the next plate, we have an example of entropy driven, where this time the signs of delta H and delta S are both positive. I got a positive delta H, which works against the sign of delta G being negative. And then we have a positive delta S of reaction, which works towards that delta G sign being negative because it's delta H minus T delta S. So if this is positive, this whole term here is going to be negative. And so in this case, delta G again is negative, and it's spontaneous as written, but we say sometimes that this is entropy driven because of the magnitude of T delta S, which is larger than the positive delta H value. Any questions on this terminology of entropy or enthalpy driven? Okay. All right. Now, in the next few slides, what we try to do is we try to make a connection between the equilibrium constant and G, Gibbs free energy. Back here, we noted in our previous equation that reactions tend to minimize Gibbs free energy, and that can take place from a product rich environment or from a reactant rich environment. So neither one of those situations is favorable according to the second law of thermodynamics, because when you have a high concentration of anything, thermodynamics says it wants to be diluted. It wants to change from pure to some mixture. And by having a mixture, entropy is increased. So we know that Gibbs free energy will decrease when there's some mixture, and it gets to that special mixture, which we alluded to back here as the equilibrium mixture. So all processes are going towards equilibrium. So now it should make sense that, old chemists never die, they just reach equilibrium. We're all heading towards it. And then once we get there, then that's it. So where were we? So we want to make this connection in a mathematical way to the equilibrium constant, okay? So one of the things we can note is that Q is non-standard conditions, or it could be actually any conditions, right? When we look at a reaction, let's say A goes to B, we can define a Q and a K. Somebody there, define me the K for this reaction. Does anybody know what the equilibrium constant for A going to B would look like?
B over A?
Yeah, concentration of the products to their stoichiometric coefficients over the concentration of the reactants to its stoichiometric coefficient. And since they're both 1, it looks like that. Now, can someone define Q?
Also B over A?
Yeah. Thank you. So what's the difference? Looks the same to me.
Is the concentrations for B and A in the K equation only for equilibrium?
Yeah, good. Thank you. Yeah, so that's the difference, right? Now, we want to look at not only equilibrium possibilities, but also ones that are off equilibrium. And you can think about this problem forever, but it's already done for you. Someone has realized that if I take the ratio of Q to K, now this Q can be any point or any concentration, right? Including equilibrium. And when it is equilibrium, then Q equals K. So what was done was said, well, we can take a ratio of Q over K. And when Q is larger than K, I'm sorry, in this case, it would be, if we look at the first one, let's do this first. When Q is smaller than K, and we take that ratio, then that ratio is going to be less than 1. And we know that the natural log of any number that's between 1 and 0 is going to give us a negative value, right? So this ratio and the log of that ratio is going to give us the right sign for delta G, because we know that when Q is less than K, there's not enough product compared to equilibrium, and the reaction should proceed to the right. Right? It's spontaneous, and delta G is negative. So that works out for the sign. And check it out for when Q is too big, when it's larger than K, we know the reaction goes to the left, or it's spontaneous in the opposite direction. So delta G should be positive in those cases. And if you follow the math and the logic, then it seems like the log of Q over K is going to give us the right sign. And the last possible option is when Q equals K, and we get that ratio of 1, then the log of 1 is 0, and that's equilibrium. So you see how this ratio of Q over K is related to the sign of delta G? Yeah?
Yeah.
Okay, cool. So you see that. So after studying this and looking at the values of delta G and the equilibrium constant for many reactions, you can see that from what we said up here, delta G is proportional to the log of this ratio Q over K. Okay. You study this for a while and you find that the proportionality constant is RT. So it turns out that delta G equals RT times the ln of Q over K. And then I can use the law of logs and say that the log of Q over K equals the log of Q minus the log of K. And so I can split that out into two terms here. And that's just using one of the law of logs. So now I have an equation that relates delta G to this log of Q value and our equilibrium constant. Okay. And so if we look at this and we say, all right, well, what happens when I have standard states here? So I want to see now what would happen if I considered a reaction with all standard states. So for concentrations, it would be 1 for all the values. So I'd have a 1 here and a 1 here, which is 1. The log of 1 is 0, so this drops out. So delta G under standard conditions, delta G 0 is directly related to the equilibrium constant. And so we get this direct relationship between the equilibrium constant and delta G under standard conditions. Any questions on that? So I essentially rationalized the equation that your book gives you for the relationship between delta G and the equilibrium constant.
In that equation, what does the R come from?
Oh, the R is a constant. It's the ideal gas law constant, but it's in units, not of liter atmospheres per mole degree Kelvin. It's in units of joules per mole Kelvin. It's 8.314 versus 0.08 to, yeah, so there's your value for R in joules per mole K.
Okay, thanks.
Yep, sure. And so this next plate, you can ignore if you want, but this was kind of my weak rationalization for how RT was derived to be the proportionality constant back here. You know, we saw, or we argued, that we get the sign right with this analogy, right, back here. But where did this thing come from? It kind of popped in, you know, and it was just given. So I went and I found some specific delta G values and equilibrium constant values. And if you look at this analogy, then the equation becomes correct when you use an RT. So in other words, if I take delta G0 for all of those reactions, and I divide that by the log of K, in every case, I get minus RT. And so that becomes the proportionality constant that makes this equation true. So if you take your calculator and you take R 8.314 and you multiply it by T, which is 298 times 8.314, you get, looks like 2.48 kilojoules. Yeah, that's right. Kilojoules per mole. I guess I should put that in there. So there's our proportionality constant for standard temperature. Anyway, this is just kind of a weak proof of where the RT pops up. Okay. But there's first principle proofs, and they involve calculus and stuff. Mine is just analyzing some experiment and showing, yeah, it pretty much comes out to be that ratio. All right, so what can you do with this equation that we found now between Gibbs free energy and the equilibrium constant? And also, what does it mean, the magnitude? We know what the sign means, but what does the magnitude of delta G? We associated it with free energy, right? That's the amount of energy that you might be able to tap into and use. But what does it have to do as far as, you know, the mixture of reactants and products? So we can get into that in a little bit more detail by looking at the next few plates. So I have this, again, this delta G that's found equal to a term involving Q and a term that involves K. So it's a difference between those two terms. And as we did before, if we consider standard conditions, then this delta G turns into delta G0. And under standard conditions, that's when the concentrations of all the reactants and products are 1 molar. So Q can be replaced with 1, and therefore that whole term drops out because the log of 1 is 0, and I get my relationship between K and delta G. All right, and so this last thing on the plate says, remember what those magnitudes of Q and K mean. When Q is different from K, that means that the reaction is not at equilibrium. Now, when Q is larger than K, that means it's too far to the right. It needs to convert some products to reactants, reduce Q until it equals K, and vice versa when Q is less than K. But the magnitude, I mean, we just talked about the relative amounts, but the larger that difference is between Q and K, doesn't that signify that those conditions are further away from equilibrium and that you're going to have to shift further to the right or to the left, depending on that magnitude of Q and how far it is away from equilibrium, those conditions? So it kind of alludes to that fact. So we know that. And then this plate just tells us how we might interpret the values of delta G and their meaning with K. Okay. So we know the sign of delta G tells us whether the reaction is spontaneous or the opposite process is spontaneous. Now, the magnitude of delta G tells us how much energy that we might be able to extract if it's spontaneous, or how much energy we would have to supply to make it spontaneous if it was possible. And that speaks to this fact that the magnitude of delta G tells you how far that standard state is when everything is 1 molar, for example, how far that is from equilibrium. Okay. So we go back and we take a look at that general equation and we try to apply that to different problems and solving different problems. So this is another form of that general equation where we substituted in delta G under standard conditions here, and that would be related to the equilibrium constant. Okay. This is a picture that tries to help understand the magnitude and the sign of delta G and rationalize it in terms of that equation that involves Q. So if we start out with all reactants, or if we started out with all products, we see that Gibbs free energy can be decreased by going in the opposite direction. So in other words, pure product or pure reactant has a low entropy, and Gibbs free energy can be reduced by having some sort of a mix. So if delta G 0 under standard conditions is large and negative, that means this process is predicted to convert a net amount of reactants to products. And that magnitude has to do with the difference between the Gibbs content of pure or standard and the Gibbs content of pure or standard product. So that's what the magnitude has to do with. But notice the equilibrium is a mixture somewhere in the middle of the pures. Well, actually not in the middle, but it's going to be leaning more towards the products in this case because the delta G is large. And we can look at it when the delta G is small and positive, then the mixture is going to go from our standard mix of 1 molar reactants and products towards making some products, but not complete products. It's going to be some mixture of those. But since it's large and positive, the equilibrium is going to be closer to the reaction complexion. So it's going to have more reactants than products. Any questions on that? Okay, so the last thing that we should do is take a look at some possible problems that use that equation that we just introduced. So predict the direction of the shift to equilibrium for this reaction at 25 degrees. So if they want you to predict the direction of the shift, then what do you have to calculate? What can tell you which way this reaction is going to shift? Which thermodynamic property? Is it delta H? Is it delta S? Or is it delta G?
Delta G.
Yeah, and once I calculate delta G, how am I going to know which way this reaction shifts?
If it's a negative delta G, it's spontaneous, so it'll shift to the right,
Yeah,
and vice
okay.
versa.
Awesome. So that's what we need to calculate, right? We need to calculate delta G. And we know from that equation, delta G equals delta G0 plus RT ln Q, where Q is the concentrations at any point in time, right? That's different from the equilibrium concentrations. All right. So in this problem, what we're going to need to do is calculate delta G and Q. And they give us Q for these two different situations. Okay. So we're going to have to calculate delta G0. Now, delta G0, we know that we can look those up, or we can use that equation that we just introduced. Remember, it was the summation of the delta G of formations of the products times their stoichiometric coefficients minus the reactants. Okay, so that's reactants. But in this case, notice that the reactants, you should know what their delta G of formation are. What is the delta G of formation of the reactants? Anybody know what it is in this case? Well, you haven't had time to work with it, but like delta G of formation, these guys are in their standard states, like delta H of formation, I mean. So the delta G of formation is going to be 0. So for this case, it's all 0. So for the reaction here, I see that it's just going to be the sum of the products, and there's only one product, so it's 2 times the delta G of formation of ammonia, which they give me. So it's 2 times minus 16.66. So the delta G under standard conditions from values that were provided from your textbook, or in this case, they give it to you in the problem, I find that this is 2 times 16.66, which is 33.3. Okay, so I have that value here. Oh, it's minus 33.3. Okay. Plus, I know that RT is, what did we say it was, like 2.48 kilojoules per mole? Oh, and this is also in kilojoules. And so now I have to do the log of Q, and I can calculate Q for these two different cases, A and B. So Q here is going to be NH3 squared, so that's 1 squared over N2, 1.47, times 1 times 10 to the minus 2 to the third, right? So Q equals you guys should check me on this. I get, oh my, 6.8 times 10 to the 1, 2, 3, 4, 5. Did anybody else get that? Okay, let's assume that that's correct. So if I take the natural log of that, that's ln q. I get over here 13.43. And if I multiply that by times 2.48, I get plus 33.3 kilojoules. So delta G equals 0 for this case. What does that mean?
Is that equilibrium?
Yeah, so that's an equilibrium mixture. So A is an equilibrium mixture. All right, how about B? Well, B is kind of easy, right? They're all ones. So that makes Q here 1 for B. So that drops out, and it just says that delta G equals delta G 0, which means it's a standard state delta G, and that's what it should be when all the concentrations for gases are 1 atmosphere. If it was a solution, it would be 1 molar. Any questions on that? So you'll be using this equation for, usually you use it for non-standard situations, or actually any calculation for delta G that might be off standard. If it's just a delta G standard calculation, then you can use the textbook values. And calculate delta G 1 from the Gibbs-Helmholtz equation. Or 2, you can use that delta G formation equation. So you sum over the products minus the sum of the reactants. So you have 2 ways that you can calculate delta G0. What happens if you're not sure, that it's at standard? Then you use this equation to calculate possible non-standard delta Gs. Any questions on that? So that last equation is a little more general. Now this question goes back to the transition temperature type problems. So it wants to know, at what temperature is the following process spontaneous at 1 atmosphere? What's the normal boiling point of liquid bromine? So here they want you to find the normal boiling point. That's the boiling point under standard conditions. So we can apply our Gibbs-Helmholtz equation for this one. And know that under this situation, there's going to be an equilibrium between the reactants and products, because that's what happens at a transition temperature, such as a boiling or a melting, boiling of a liquid or a melting of a solid. We know that delta G is 0 because there's an equilibrium there. And so we can go ahead and use our book values to calculate delta H of reaction from the delta H of formations. We can calculate the delta S of reactions from the absolute entropy values that are in your textbook. And once we have that, then we have everything we need to calculate that transition temperature. So try that, make sure you get that answer. Remember a couple of the sticky points when using these equations is that G and H are in units of usually kilojoules per mole, whereas S, the units in your textbook and online, are usually joules per mole Kelvin. So when you combine them in this type of equation, you're going to have to convert either delta S from joules to kilojoules, or delta H from kilojoules to joules. But keep your units straight. And also don't forget, if you're going to put in a temperature, then it's got to be in Kelvin. If you're going to calculate a temperature, then it's going to come out in Kelvin. Okay. All right. Now this last problem asks you to find the equilibrium constant given a delta G of the reaction. And we know what the relationship between delta G and the equilibrium constant is now. From our previous discussion, we know that delta G0 equals minus RT ln K. So if I want to calculate K, I know that ln K equals minus delta G over RT. And I wanted to get rid of that ln, so I used the anti-function, or the e to the ln. These guys are anti-functions, they wipe out, so I get k equals e to the minus delta G over RT. I can take this value, plug it in here, but I'm going to have to do a conversion either of the delta G and convert that to joules, or I'm going to have to convert, 8.314 joules per mole K. I'm going to have to convert that from joules to kilojoules. So I have to watch out what I'm doing here and not mix up the units. Okay, so you guys, I think you can plug and chug on that. And that wraps it up for thermodynamics. And so we'll end it there. Are there any questions on this or anything?
I have a question for the example that we did for number one, the predicting the shift. When we use that delta G zero equation with like the summation and so I guess we couldn't also use this delta G zero equation because they didn't give us K, or we couldn't find K.
Yeah, which one are you referring to? Is it one back here that we looked at?
Yeah, it was the number one. Yeah, that one.
Oh, sorry. Okay, so this guy right here that has the equilibrium mixture.
Oh, that's the equilibrium. Oh, okay. Could we have used, because I see in this one, the delta G zero formula is like the summation of delta GF products minus summation of delta GF reactants.
Uh-huh.
And then I see another delta G zero is equal to negative ln K or RT.
Yeah, so that's what we found out with the delta G under standard conditions. That's signified by that superscript 0. That is when all the reactants and products are under standard conditions. Now, what's standard conditions for delta G? We just introduced that back here. And so let's take a look at this. Oh, right there. So the standard conditions for Gibbs free energy, it's pure for a solid or a liquid, 1 atmosphere for a gas, and if there's a solution, then it's 1 molar concentration. So that's the standard states. So if we go back to that problem of A and B, there we go. Then we see that B is the standard states for this reaction, where the gases are all 1 atmosphere. So Q is 1, and this term drops out. And so it's not surprising that we get delta G 0, that's standard state, equals that delta G that we're trying to calculate. It's a standard delta G.
Okay.
Now, the first one that we calculated, we used the standard delta G in this position for that A mixture, and we calculated that by just using this equation here for the summing of the delta G of formations of the products minus the reactants. And then we added to that RT times LNQ. It's kind of like a correction factor for being off standard, right? Because the only time you get a contribution from this term is when Q is not 1. It's the reaction mixture is something that's not standard. So we put these values in here, which are not standard values, and it turned out that what they were equilibrium values, because when we calculated the RT ln Q, it equaled an opposite sign of the standard delta G. So then we recognize this as being equilibrium concentrations. We could have put in some other values, and delta G would have been, this delta G over here would have been positive or negative. And then we would have known that that mixture complexion was to the right or to the left of equilibrium.
Okay, so we couldn't have used the negative RT LNK because we didn't know that they were in equilibrium.
Yeah, that's right. Because we were saying, given this mixture, which way is this reaction going to proceed? Is it spontaneous to the right or spontaneous to the left, or is it at equilibrium? So at A mixture, it's at equilibrium. B mixture, it turns out that this is the standard state mixture, where I get a delta G value of minus 33.3. It's negative. So this delta G equals delta G standard, which is minus 33.3 kilojoules. And that tells me that under these standard conditions, this reaction is predicted to proceed to the right towards products. And I might be able to extract something less than 33.3 kilojoules if I can tap into that free energy that's being given off.
Okay, that makes sense. Thank you.
Thanks for asking. Any other questions? All right, then I guess I'll quit now, and I'll just take any specific questions if you guys have any.